Hello, myself Mrs. Anjali Nadgouda, lecturer, Department of Chemistry, KLS Gokte PU College of Commerce and Science, Belgavi. In continuation with unit number 4, Chemical Kinetics, this is fourth video. In today's video, we will learn integrated rate equation for first order reaction. Now this is in gaseous phase reaction, means in which the reactant and products both are in gaseous state. In earlier class, that is earlier video, we have seen integrated rate equation for zero order reaction and first order reaction. So here we will see first order gas phase reaction. Okay, consider a first order gas phase reaction of the type A gives B plus C. So here reactant is A and product is B and C, which are in gaseous phase. Okay. So let Pi be the initial pressure of A. See, for gaseous reaction, instead of concentration, pressure is considered. Okay, and that is atmospheric pressure. Okay, and Pt is the total pressure at time T. Okay, then for such reaction, integrated equation can be derived as, first of all, we have to take total pressure Pt as a Pa plus Pb plus Pc, that is partial pressure of individual gases. This is according to Dalton's law, that which we have learned last year. Okay. Then next, where Pa, Pb, Pc are the partial pressures of A, B and C respectively, in which A is reactant, B and C are product. Okay. Suppose if X atmosphere pressure is decreased during the reaction, now this decrease will be for reactant A, okay, at time T. Then that much pressure should increase in formation of B and C. Let us consider it is for 1 mole of each B and C. So the increase in pressure of B and C will be also X atmosphere each. This ATM is atmosphere. Okay. Then the equation A gives B plus C. Here we are taking at T is equal to 0. Pi is the initial pressure, then initial pressure of B and C is 0 atmosphere. Okay. At time T, what happens? Now at time T, X atmospheric pressure is decreased of reactant. So Pi minus X, and that much will be for B and C. That much will be increase for B and C. So 0 is increased to X and 0 is increased to X. Okay. Then where Pi is the initial pressure at time T is equal to 0, then Pt is given as, according to first equation I told you, Pa plus Pb plus Pc. So it will be given as Pa is equal to Pi minus X, Pb is X and Pc is X. Okay. So Pi, now here minus X this minus X, this minus X and this plus X get cancelled. So what remains? This is Pi plus X. Okay. Then next one, X is equal to Pt minus Pi. Okay. Then where Pa is equal to, if we consider individual pressure of reactant A, it is given as Pi minus X. So substituting the value of X, that is Pi minus Pt minus Pi. Okay. So this Pi and this Pi, this is minus minus become plus, this minus and this minus will become plus. So Pi plus Pi become 2 Pi and this is Pt. So 2 Pi minus Pt is the individual pressure of A, reactant A. Okay. Then K, rate constant, can be given as 2.303 divided by T into log of, as we were taking for first order reactant, okay, that was R naught by R, like that here Pi divided by Pa will come. So we will substitute the value of Pa as 2 Pi minus Pt. So the final equation becomes K is equal to 2.303 divided by T into log of Pi divided by 2 Pi minus Pt. Okay. So this is the integrated rate equation only for gaseous phase reaction. Means whenever the pressure is given, we can use this equation. Otherwise, if the concentration is given, we have to use the earlier integrated rate equation for first order reaction. Okay. Yes. Next. So we will solve some problems based on average rate, because already we have learnt what is average rate or instantaneous rate. So we will take the problems. For the reaction, R gives P. The concentration of a reactant changes from 0.03 molar, capital M is molar, to 0.02 molar in 25 minutes. Time is given. Calculate the average rate of reaction using the units of time both in minutes and seconds. So here the solution, average rate of reaction is given as minus delta R divided by delta T. Now why minus sign? Already I told you, because during the reaction the concentration of reactant always get reduced. Okay, so minus sign. D, delta stands for any small change for the given time interval. Okay. R, square bracket R is molar concentration of the reactant. Okay, and delta T is nothing but what? Change in time or whatever interval of time is given, right? So average rate of reaction formula is delta R can be calculated as R2 minus R1, that is final concentration minus initial concentration, divided by delta T is given by T2 minus T1. Now according to this problem, the two concentrations are given, that is initial and final. Okay, R2 and R1 value are given, but T2 minus T1 is directly given as 25 minutes. Okay, so 0.02, because the concentration is reducing. So 0.03 is initial concentration and 0.02 is final concentration. So 0.02 minus 0.03 divided by 25. Now this value will come minus, and again minus sign is there. So minus minus will become plus, and the final value will come as plus. Okay. So divided by 25 will get 4 into 10 to the power minus 4. This is molar concentration, because unit will come as what? Concentration and time. Concentration divided by time. Okay. So molar is the concentration of numerator, that is unit, and per minute is the unit for time. Okay. Now this is in minute, but in given problem the rate, average rate, is asked to calculate in seconds also. Okay. So to calculate it in seconds, we have to again divide by 60. Okay. So 4 into 10 to the power minus 4 divided by 60, that will come as 6.667 into 10 to the power minus 6 molar per second. Okay. Next, in a reaction 2A gives P, the concentration of A decreases from 0.5 mole per liter. Instead of molar concentration capital M, here what is given? Mole per liter. Both are same, remember, to 0.04 molar per mole per liter in 10 minutes. So here time interval is given as 10. Calculate the rate during this interval. Now, according to reaction, 2A gives P. So, average rate is given as what? Minus half. This is, we have seen in general reaction of the type AA plus BB gives CC plus DD. Okay. So, how we can write? Average rate of reaction is given as minus half into delta A divided by delta T. Now, delta A, that is change in concentration, is given as A2 minus A1 and delta T is given as T2 minus T1. But here delta T is already given, that is 10 minutes. Okay, so directly we can take this value. Now, how the concentration is changing? From 0.5 to 0.4. Okay, so A2 is 0.4 and A1 is 0.5. So, 0.4 minus 0.5 divided by 10 into half. Okay, why we have taken half? Because here 2 moles of A is given. Okay, therefore we have taken half. Then minus minus become plus, and what will be the value? 0.005 mole per liter per minute. Now, why per minute? Because the time is given in minutes. Okay, therefore it will come as mole per liter per minute. Instead of mole per liter, we can write this as capital M. Okay, and if you want to convert this into scientific notation, it will come as 5 into 10 to the power minus 3 molar per minute. Okay. So, these are the sample problems based on average rate. Okay. Now, based on the rate constant, which we have seen in integrated rate equation of 0 order and first order. So, here we will solve the example of or the problem based on first order reaction. Okay. The problem is given the initial concentration of N2O5 in the following first order reaction. Already the order of the reaction is given, that is first order reaction. Okay. Concentration is given, initial concentration 1.24 into 10 to the power minus 2 mole per liter at 318 Kelvin. The concentration of N2O5 after 60 minutes was 0.20 into 10 to the power minus 2 mole per liter. Means this will be R and this will be R0. Okay. Calculate the rate constant of the reaction at 318 Kelvin. Though in this problem temperature is given, remember we are not considering, or no need to consider the temperature in this while solving the problem. Okay. But see to it that both the concentration are at the same temperature. Okay. So, which formula we can use? Integrated rate equation for first order. K is equal to 2.303 divided by T into log of R0 divided by R. Okay. Now, here though these reactant and products are in gaseous state, but we cannot use the integrated rate equation for gaseous phase, because here the concentrations are given in mole per liter, not the pressures are given. Okay. Yes. So, K is equal to 2.303 divided by 60 minute, time is given in minute. Okay. Log of 1.24 into 10 to the power minus 2 mole per liter, and next concentration is 0.20 into 10 to the power minus 2 mole per liter. Okay. Now, if you solve this, just see, this 10 to the power minus 2, this 10 to the power minus 2 will get cancelled. What remains? 1.24 divided by 0.20. This will come as 6.2. Okay. So, by seeing the log table, we can find out the value of log as 0.792. Okay. So, 2.303 divided by 60 into 0.72, the final answer will come as 0.0304. Now, here as the unit of time is given in minute, we have to write the rate constant unit as per minute. All of you know it, for first order reaction, the rate constant unit is per second. Okay, but as the time is given in minute, here we are using the unit as per minute. Okay. Yes. There are some more problems in textbook, you can go through that. Now let us start with half-life of a reaction. What is meant by half-life of reaction? See, whenever we conduct or whenever we carry out any reaction, okay, the concentration of reactant is always reduced and the concentration of product is always increased, right? Means now here the time required to reduce the concentration to exactly half of the initial concentration is nothing but the half-life of the reaction. Half-life means exactly 50%. If you take 1 gram, when the reactant is reduced to 0.5 gram, then that time is called as what? Half-life. Okay. So usually the radioactive elements are the half-life period of radioactive element is measured. Why? Because they are always decaying. Okay, it's a natural process. Radioactive elements are always decaying and it is always first order reaction, because we have already learned the example of first order reaction as radioactive decay, and therefore the half-life period of radioactive element is calculated and from that its life is measured. Okay. So what is the definition of this half-life reaction? Half-life of a reaction is, the half-life of a reaction is the time in which the concentration of a reactant, remember it should be a reactant, is reduced to 1/2 of its initial concentration, and it is represented as T half. Okay, this half should be written as subscript, or else one more definition is given. The time taken to complete the reaction by 50% is called as half-life period. Okay. Now we will again, there are two derivations for zero order reaction and for first order reaction. So let us start with zero order reaction. Derivation for half-life period of zero order reaction. Okay. So how the rate, we know that rate constant of zero order reaction is given as R naught K is equal to R naught minus R divided by T. This is the integrated rate equation for zero order reaction. This is already we have learned in last video. Okay. If you want, you can go through last video once again. Now at this time, at time t, at exactly half-life, means when the concentration of the initial concentration will reduce to half, t will be t half. Okay. Or let us consider at t is equal to t half, exactly at half, R will become R naught by 2, means initial concentration will be reduced to half. Okay. It can be written as R naught by 2 or half into R naught. Okay, both are same. Now rate constant at T half becomes, so R naught minus, instead of R, what we have to write? R naught by 2. So here when we are writing R naught by 2 or half into R naught divided by T half. Now taking this T half on this side and K we will bring it at the denominator. So T half is equal to R naught minus half R naught. R naught minus half R naught will become what? Half R naught, means we can write it as what? R naught by 2. Okay. So R naught by 2 when we are writing, we have written here, then K will come this side, right? So 2K will come. Now what is the expression then? T half is equal to R naught by 2K. Now if you see this expression, it is clear that this 2 is constant, K is constant because it is a rate constant. So denominator term is constant. What is remaining? Only initial concentration. Okay. So if you remove this K, T half will be what? T half will be directly proportional to R naught. That is, it shows that what? Half-life period for a zero order reaction is directly proportional to the initial concentration of the reactant and inversely proportional to the rate constant. Okay. Now this question can be asked for 2 or 3 marks. Derive the expression for zero order half-life period of zero order reaction, or based on this maybe the problems asked. Okay. Similarly, we will see for first order reaction. Now we know that integrated rate equation for first order reaction is K is equal to 2.303 divided by T into log of R naught upon R. Okay. Now again at T is equal to T half, R will become what? R naught by 2. Again this step is same. Okay, as like zero order. So rate constant at T half becomes K is equal to 2.303 divided by T half. Instead of T, what we should take? T half into log of R naught divided by R naught by 2, because this R will become what? R naught by 2. Now this is denominator to denominator. So this 2 will come to numerator. Okay. This 2 will come to numerator, and this R naught get cancelled. What is remaining? T half is equal to 2.303 divided by K into log of 2. Okay, log of 2 is nothing but what? 0.3010. By seeing the log table, you can find out the value of log 2. So it will come as 0.3010. Sorry, here there should not be, this should be cancelled. Okay, log should not be there. Directly the value of log of 2 is substituted and it is multiplied. Okay. So 2.303 divided by K into 0.3010. That will come as 0.693 divided by K, and this is the equation for half-life period of first order reaction. Okay. Please cancel this log here. This is not required. Instead of that, multiplication sign is required. Okay. Now, from all this, what we can observe? It can be seen that for a first order reaction, half-life period is constant. That is, it is independent of initial concentration of the reactant species. Why? Just see here, is there any term of R in the final expression? Not at all. And hence, T half, that is half-life period for first order reaction, is independent of initial concentration. And the question is asked like this only. Either derive the expression for half-life period of first order reaction, or else show that the half-life period of first order reaction is independent of initial concentration. So after this expression, you have to write this sentence, first sentence. Okay. Then half-life period of first order equation is calculated readily from rate constant and vice versa. So here the conclusions are given, and we'll stop it here. Thank you.